Today we shall study about magnetostatics. In the magnetostatics, we shall study about the common properties of magnetism and the magnetic material. Number one, the earth behaves as a magnet with the magnetic field pointing approximately from the geographic south to north. Second, when a bar magnet is freely suspended, it points in north-south direction. The tip which points to the geographic north is called the North Pole, and the tip which points to the geographic south is called the South Pole of the magnet. There is a repulsive force when North Poles or South Poles of the two magnets are brought close together. Conversely, there is an attractive force between the North Pole of one magnet and the South Pole of the other. Fourth, we cannot isolate the North Pole or South Pole of the magnet. If a bar magnet is broken into two halves, we get two similar bar magnets with somewhat weaker properties. Unlike electric charges, isolated magnetic North Pole and South Poles, known as magnetic monopoles, do not exist. It means the North Pole and South Pole are jointly forever. It cannot isolate from each other like charges as positive and negative charges in the electrostatic or current electricity. So, it does not exist separately. Therefore, we can say that magnetic monopoles do not exist. It is possible to make magnets out of iron and alloys. Now the magnetic field lines flowing from the north and south pole. The magnetic field lines are a visual and intuitive realization of the magnetic field. Their properties are: the magnetic field lines of a magnet or a solenoid form continuous closed loops. This is unlike the electric dipole, where these field lines begin from a positive charge and end on the negative charge or escape to infinity. The tangent to the field line at a given point represents the direction of a net magnetic field B at that point. The larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. In figure 1, B is larger around region 2 than in region 1, as shown in the figure. Now, the magnetic field lines do not intersect, for if they did, the direction of the magnetic field would not be unique at the point of intersection. Footnote: in some books, the magnetic field lines are called magnetic line of force. This nomenclature is avoided since it cannot be confusing. Unlike electrostatics, the field lines in magnetism do not indicate the direction of the force on a moving charge, as shown in figure A, B, C. The figure 1A, the field lines of a bar magnet, and B, a current carrying finite solenoid, and C, the electric dipole. At larger distance, the field lines are very similar. Labeled 1 and 2 are closed Gaussian surface. Now the bar magnet has an equivalent solenoid as shown in figure 1A and B. Now let the solenoid of the figure 1a consists of enters permanent length. Let its length be 12. Let its length be 12 and radius A. We can evaluate the axial field at a point P at a distance R from the center O of the solenoid. To do this, consider a circular element of thickness dx of the solenoid at a distance x from its center. It consists of n dx terms. Let L be the current in the solenoid. Now the magnitude of the field at point P due to circular element is dV is equal to mu naught n dx by mu naught n dx I a square bata 2 into r minus x का whole square plus a square whole to the power 3 by 2. The magnitude of the total field is obtained by summing over all the elements. In other words, by integrating from x power minus L to x power plus L. Thus, B बराबर mu naught n I a square by 2. So, integral from minus L to L dx बटा r minus x का whole square plus a square whole to the power 3 by 2. Note that the range of x is from minus L to plus L. Consider the far axial field of the solenoid. It means r is very greater than a and r is very greater than L. Then the denominator is approximated by r minus x का whole square plus a square whole to the power 3 by 2 is equal to r cube. And b बराबर mu naught n I a square बटा 2 r cube integral minus L to L dx बराबर mu 0 n I by 2 into 2 L a square by r cube. That is equation number 1. Note that the magnitude of the magnetic moment of the solenoid is m. So m, the dipole moment is equal to n into 2L I pi a square. It means it is the product of total number of turns guna current guna cross sectional area. Thus B बराबर mu 0 बटा 4 pi into 2m बटा r cube. That is equation number 2. This is also for the axial magnetic field of a bar magnet which one may obtain experimentally. Thus, a bar magnet and a solenoid produce similar magnetic fields. The magnetic moment of a bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic fields. Note, magnetic dipole moment M associated with a current loop was defined to be M बराबर n I a, wherein is the number of turns, I is the loop current, and A is the area vector. Magnetic monopoles do not exist. It means that any magnet whose north and south pole can be separated do not exist in the world.